All right. So, an application of triple integrals is being able to find the volume of an object that we have, and we can find the volume of this by just taking the triple integral of every function that we have. And so our function is going to be defined by basically our bounds for our integrals. All right. So we're able to um, find the volume of any object as long as we can define the integral in which they are in. So let's go ahead and write out what we have. So we want to find the volume of the solid enclosed by the cylinder x squared plus z squared equals 4, and the planes y equals -1 and y plus z equals 4. All right, so we already have the planes that we're going to be in between. So our outside integral is going to be, or not, sorry, our main integral on the inside, the area in between, or the shape, the object is going to be between the two planes, y equals -1 and y plus z equals 4. So what we can say is, oh, okay, my triple integral is going to be we'll go ahead and define this as our our integral and our double integral for d. We're going to go ahead and take the the first integral first, which we're going to make between -1, and we can solve this equation for y as y is equal to 4 minus z. And then this will be of dy and then dA, which will take care of the outside. So let's go ahead and integrate that. When we do that, we're going to get the integration of just, y 4 minus z and -1 dA. And then we have four minus z minus -1. And so we're going to get the double integral of, then we can say, okay, 4 minus z minus 1 is just going to be 5 minus z. All right, now what I can say is I have x squared plus z squared equals 4. That's going to be that's just going to give me a circle on the xz plane. All right, where I can say x is equal to r cosine theta, and that means that z is going to be r sine theta. All right, instead of being instead of y being r sine theta, we can make z equal to r sine theta. And again, that is as long as, when we do this, this is going to be the x and that's going to be the z, which is going to take the place of the y. All right, and so looks like we have a radius of 4. I'm sorry, a radius of 2 if x squared plus z squared equals 4. So we're using spherical, we're going to be able to use our polar coordinates, but instead of, xy, on the xy plane, we can now put these on the xz plane. And so that means that x squared plus z squared is equal to r squared. All right, so now I'm going to change this up to be the double integral, and it looks like for theta, our circle is going to be it's going to be a full rotation, so 0 to 2 pi. Our radius looks like it's going to be, at 2, so between 0 and 2. And then our function 5 minus z is going to be 5 minus z. Z is going to be r sine theta. And we have to write r dr. d theta. So when we can put these in spherical coordinates, we want to, because it makes our life easier. So now I'm going to break up the integration from 0 to 2 pi d theta. And then I'm going to go ahead and distribute that r in there. So from 0 to 2, and then we're going to have 5r minus r squared. Oh, I'm sorry, I can't break up the integration because I have that sine theta there. So let's not break it up. All right, so let's go ahead and distribute that r. So I'm just going to go ahead and distribute it inside there. And so we're going to have r squared, and then r and r squared. All right, so we have from 0 to 2 pi. Let's go ahead and integrate with this. So I'll have 5 halves. It's ugly 5 halves. So 5 halves r squared minus 1/3 r cubed sine theta from 2 to 0 d theta. And so then I'm going to have the integral from 0 to 2 pi. Plug in 2, so 2 squared is going to be 4. 4, taking that, so it's going to be 10. Minus 1/3 r cubed. R cubed is 8, so minus 8/3 sine theta. From 0, so d theta. All right, now let's integrate with respect to theta. So we're going to go ahead and have 10 theta minus, plus 8/3 cosine theta. Now let's go ahead and plug in for theta, which is going to be plug in 2 pi. We're going to get 2, so 20 pi plus 8/3 minus, plug in that 0, so minus 0 plus 8/3. 8/3 is going to cancel out, and we're left with just 20 pi. All right. So again, we can change the spherical coordinates just as long as we make sure that we can move this to the xz plane, just making sure that we keep x or y the same. So if we move to the yz plane, y would